Good afternoon, everybody. Thanks for attending. My name is David Churchill, and I'm going to talk to you a little bit about how inertial sensor technology can be used in robotics applications, particularly for attitude sensing and even in some cases for navigation. Over the last several years, inertial sensor systems have become available which are quite small, low cost, low weight, low power consumption, and have quite good performance. This, for example, is MicroStrain's 3DM-GX3 sensor, which has these qualities. Inertial sensors comprise two different types: accelerometers, which measure linear acceleration, and angular rate sensors, or sometimes called gyroscopes or gyros, which measure angular rate, that is, the rate of rotation. The principle of operation is Newton's second law, which is force equals mass times acceleration. Now, this is clear that accelerometers should use this principle. That is, if there's an acceleration present and there is a proof mass, then the force generated can be measured and provides the output. You might think for the rate sensors that the rotational analog, that is, torque equals moment of inertia times angular acceleration, would be the operating principle. However, this is actually not the case. There are sensors that do use this principle. Those are called angular accelerometers. However, those are generally not very good performing in practical applications. Angular rate sensors use the Coriolis effect in combination with Newton's second law, that is, force equals mass times acceleration, to effectively sense angular rate. So if you look at a system that's built using triaxial accelerometers and triaxial angular rate sensors, what you'll see is that that device can measure 3 angular rates and 3 accelerations, as illustrated in this diagram. You see that these quantities are measured with respect to the coordinate system, the local body fixed coordinate system, fixed to the sensor itself. This is called a strap-down configuration because that sensor is presumably mounted to an object, for example, a vehicle, which may rotate as it moves in space. And the sensor moves with the vehicle, and therefore the measurement axes move with that vehicle. So the accelerometers measure in the linear domain, while the angular rate sensors measure in the rotational domain. And it's interesting to note that the acceleration measurement is the second derivative of position, whereas the angular rate is the first derivative of angular position, otherwise known as attitude. And this becomes important, as you'll see later on, when we're trying to derive position or attitude from the acceleration and angular rate, because the more integrations needed, the more potential for errors to creep into the system. Inertial sensors in general have advantages and disadvantages. And when you're selecting what needs to be used in a particular application, you will want to consider these. One of the main advantages of inertial sensors is the fact that they're completely self-contained and cannot be influenced by any external means. That is, the signal cannot be jammed, they can't be blocked in any way. And this, of course, is one of the reasons why the military values inertial sensors to a high degree. Also, now, small, self-contained, low-cost MEMS inertial sensors are widely available. The performance of these is increasing every year, and this makes their use very attractive. On the other hand, one disadvantage of inertial sensors is that their direct output, that is acceleration and angular rate, often are not what is actually wanted as the measurement output in many applications. And we'll talk about this in a minute. Another disadvantage is that because of the fact that you have to process the results to get the quantity that you're actually interested in, you bring about the opportunity for drift to enter into the results. And this is one of the characteristic problems with inertial sensors. So just to make it a little bit more tangible, I've taken a photograph of several types of inertial sensors, that is MEMS inertial sensors, that are available on the open market today, that are used by outfits like Microstrain and others. And on this photograph here, you can see several different gyroscopes and several different accelerometers. Whether or not an inertial sensor performs well in any particular application depends a lot on the nature of that application itself. Some applications are quite favorable, and the most favorable are those applications where what is needed is a measure of the linear acceleration and/or angular rate itself. These are, of course, as I mentioned, the direct outputs of the inertial sensors themselves. And sometimes this is the case. For example, Microstrain had a customer not too long ago that needed to quantify the ride quality of a roller coaster that they operated. And what they wanted was measurements of the angular rate as the roller coaster rounded corners and the acceleration as the roller coaster went over heaves in the track. And this was quite a favorable application for our inertial sensors. They worked well and the customer was quite happy. More challenging applications are those in which the quantity of interest is something else besides the angular rate and acceleration. And typically that would be either an attitude solution, that is the host system would want an attitude reported, which is the pitch and roll and potentially the heading of the device, or a navigation solution in which the position is desired, that is potentially expressed as a longitude, latitude, and altitude measurement. Now, if that's the case, then a processing algorithm of some kind is needed, and quite often this is called a filter, although it shouldn't be confused with the more conventional low-pass filter, for example. This is really a processing algorithm. So in a system which includes such a processing algorithm, the system would have several blocks in the big picture block diagram. First, the basic sensors are there, and the raw measurements would be captured periodically. And then those raw measurements would be passed to a portion of the operating software which scales that data using calibration coefficients. And that produces essentially the direct output of the system, which is the acceleration and angular rate. Now, the processing algorithm then would take the acceleration and angular rate, perform some processing, that is, carry out an algorithm to create a new data quantity in potentially an attitude solution or in some cases a navigation solution. So the important concept here is that some new piece of information is being formed that was not directly measured by the sensors themselves. Now, in the rest of this presentation, I'd like to go over at a relatively high level how an attitude solution or a navigation solution is formed. And in particular, I would like to highlight the differences because it turns out that computing an attitude solution makes use of the fundamental sensor outputs in a manner which is quite different than if you're computing a navigation solution. And understanding that difference, I think, is really helpful as a customer trying to make sense of the outputs that are coming out of your sensor, and in particular, choosing which sensor might be appropriate for a particular application. So on this slide, I have some bullet points showing the differences between an attitude solution and a navigation solution. So an attitude solution, the goal of an attitude solution is to estimate the pitch and roll of the device and potentially also the heading. Now, when you set out to do this, you can create an algorithm in which the errors can in fact be bounded. That is, there may be errors that might not be perfect, but the errors will not grow indefinitely and become very large. Carrying out this kind of algorithm is what I would characterize as moderately demanding on the sensor performance. Now, on the other hand, computing a navigation solution is one in where you're trying to compute the position of the device on the surface of the Earth, essentially. So your output would be a longitude and a latitude and an altitude or some equivalent metric. It turns out that when you do so, along the way, you need to compute the velocity, and in fact, you also need to compute the attitude. In this case, when you're computing a navigation solution, the errors cannot be bounded if you're just using accelerometers and gyroscopes. It turns out they can be bounded if some other additional aiding sensors are available, and I'll talk about that a little bit at the end of the talk. But with a navigation solution, the errors that creep into the system can continue to grow in such a way that they become larger and larger and larger without any limit. And the result of this is that computing an accurate navigation solution is, in fact, very demanding. So let's go over the steps required to generate an attitude solution. So first of all, you can notice that it is, in fact, possible to create an attitude solution using just the angular rate sensors. So we say that the angular rate sensors can provide one estimate of attitude. And that estimate simply is formed as a time integral of the measured angular rates, as shown on this slide. Now, when you do this estimate of attitude using only the gyroscopes, there is a characteristic error that will typically be observed, and that is if the gyroscope has a bias error, then the estimated attitude will contain an error which grows linearly with time. So a bias error is, or the bias is the output of the gyro when there is in fact zero angular rate, true angular rate input. So if normally a perfect gyro would read 0 if there's zero angular rate. If there's an error in the bias, it would not read 0, but instead would read some slightly non-zero number, for example, possibly 1/100th of a degree per second. And under those conditions, when you time integrate that output, you will in fact get an attitude error that grows linearly with time, as shown on the graph. On the other hand, at the same time, the accelerometers can provide a second estimate of attitude. And this is because the accelerometers measure the gravitational acceleration in addition to the linear acceleration that the device might be undergoing. So in other words, whatever the accelerometers measure is always a combination of the gravity vector plus whatever linear acceleration is present. So that means that if there is zero acceleration, that is zero linear acceleration, in other words, if the device is stationary or if it's moving at a constant speed, then under those conditions, the accelerometers will be measuring only the gravity vector. And as you know, the direction of the gravity vector essentially defines the vertical direction. So an attitude can be estimated simply from the measured acceleration vector. And that estimate is formed essentially as the angle between the vector, that is the measured acceleration vector, and the body fixed coordinate system of the device. Now, that estimate of attitude has a different characteristic error. And that estimate will have errors if, in fact, there are linear accelerations actually present. So, in other words, if your device is shaking back and forth, as represented here, then the measured acceleration vector will not be in the vertical direction because it will be a combination, that is a vector sum of the gravity vector plus whatever linear acceleration is present. And typically what happens is you'll see that linear accelerations will be oscillating back and forth, and so the direction of the measured acceleration vector will be oscillating back and forth. So what we have is two fundamentally independent estimates of attitude. And here we look at the characteristics of those two different estimates. So on the one hand, the angular rates sensors estimate is, first of all, it's incremental. That is, it cannot know its absolute attitude. When you turn the device on, it doesn't know where it is. All you can measure is where you've changed from where you started. Really, though, the bigger problem is that gyroscopes are subject to drift errors, generally caused by bias errors. However, they do perform well in highly dynamic conditions. In other words, if your system quickly rotates 93 degrees, for example, your gyroscope will quite likely measure that very accurately. So one way to say this is to say that in the high-frequency domain, that is, if the actual motion input has high-frequency content, the gyroscopes would be expected to be accurate. On the other hand, in the low-frequency domain, those gyroscopes would expect it to be not accurate. In other words, it's difficult for a gyroscope to distinguish between drift caused by bias, which is an error source on the one hand, and actual slow motion, true motion. Now, going to the accelerometer estimate, first of all, we can see that the accelerometers produce an estimate of attitude, which is in fact absolute. So they know relative to the fixed Earth what their attitude is. They do not drift over time. There is no problem with the accelerometer estimate moving gradually in time. And they do perform well in static conditions. However, as we saw in the previous slide, they do not perform very well under highly dynamic conditions. So what we can say, if we look at the frequency domain performance of the accelerometer-based estimate, we can see that the high-frequency performance is not accurate. That is, if the actual input contains linear accelerations at a relatively high frequency, the accelerometers do not produce an accurate estimate of attitude. However, when the input motion has low frequency content, they do produce an accurate estimate of orientation. So a very important concept is that these two independent estimates of orientation or attitude can in fact be combined to form a best estimate, which is better than either of the two starting estimates. And the way you do that is you capture the high frequency content from the gyros and combine that with the low frequency content coming from the accelerometers. And doing so is essentially a description of what's called a complementary filter. So in the graphics at the bottom, you can see that the attitude estimate from the gyros, theta sub g, would be passed through a high-pass filter to remove its low-frequency content, yet retain its high-frequency content. At the same time, the attitude estimates coming from the accelerometers, theta sub a, would be passed through a low-pass filter, and therefore its high-frequency content would be removed while the low-frequency content would be retained. Those two signals then are simply combined to perform or to produce the best estimate of attitude. Now, when you actually try to implement this kind of filter in a program operating on a device, this is a high-level view of what you actually need to do. So first of all, your program will operate in a continuous loop where every iteration you'd make sensor measurements and then you compute these quantities. First of all, the accelerometer-based estimate of attitude is computed simply as the direction of the measured acceleration vector at that instant in time. Next, you need to compute the gyro-based estimate of attitude. And this is a little more subtle. And first of all, you start with the best estimate of attitude from the previous iteration through the program. And you add to that the time integral of the angular rate signal that has occurred since that previous time increment. And you add those together, and that produces your current estimate of the gyro's attitude. So once you have those two independent estimates of attitude, you can combine those using a simple weighted average. So on the bottom line, you can see that the best estimate of attitude is a simple weighted average of the two independent estimates of attitude. The factor K is the weighting factor. Now, I've also got delta T in here, which simply represents the program's iteration time, and that needs to be in there to normalize things. So K is the weighting factor, which this is a weighted average. So the weighting factor is used to determine essentially how much each of the two independent estimates gets added and blended into the final best estimate. K is also sometimes called a gain, especially when you're talking about common filters. And K is essentially a measure of the crossover frequency that the high-pass and low-pass filters are controlled by. And you can also think of the inverse of K as being a time constant. So the properties of a complementary filter then are the following. First of all, the gyros and accels each provide an independent estimate of attitude. And then a weighted average is formed of these two estimates to produce the best result. So ideally then, the best properties of each estimate is retained, while the worst properties of each of the estimates are rejected in forming the best estimate. One of the important results of this is that the errors are in fact bounded in most situations. So whereas the gyro-based attitude estimate can in fact be unbounded, the errors being unbounded, when you combine it with the accelerometer-based attitude estimate in the form of a complementary filter, the resulting best estimate of attitude is generally bounded, so the errors will never grow beyond a certain amount. Now, there are some limitations in a complementary filter design, and one thing that might not be apparent is that there is a fundamental assumption that is being made in the formulation of this filter design. And it's, if you say that in words, what essentially the assumption is that the long-term average of the measured acceleration vector is equal to the gravity vector. So that's an assumption that's essentially being made. Now, the phrase long-term average is a little bit subjective, but essentially think of that as long-term relative to the time constant, which again is the inverse of the weighting factor. So the problem happens when this assumption is violated, and this assumption is not always true depending on the application. And any time that the device, the sensor, is exposed to conditions that simulate a centrifuge, this assumption will be violated. And so in a vehicle application, whenever you have a vehicle that's undergoing sustained high G turns, you can have problems. And keep in mind that this only happens when high G turns are sustained in time. The result of this type of error is that the attitude estimate will accrue errors of such a type that the roll and pitch associated with that turn will erroneously begin to drift towards zero. Okay, so we just reviewed at a relatively high level how you can form an attitude estimate using an inertial sensor that has accelerometers and gyroscopes. So now let's go ahead and take a high-level look at how you can form a navigation solution using the same sensor that has accelerometers and gyroscopes. So let's go over the basic steps as shown on this slide. First of all, it turns out that the first thing you have to do to compute a navigational solution is to start out by estimating the attitude. Then you use that attitude to mathematically rotate the measured acceleration vector into the navigation coordinate system. So the navigation coordinate system is generally a coordinate system that's fixed to the Earth. So it has, for example, a vertical z-axis and horizontal x and y axes. This is in contrast to the body-fixed coordinate system associated with the sensor, which may move and at any time be oriented in any general direction. So once you've rotated that acceleration vector, the next thing you need to do is subtract the known gravity vector from the measured acceleration vector. So this is because you want to integrate the linear acceleration measurement twice to get position. But you know that the measurement that the accelerometer makes contains the gravity vector as well as the linear acceleration. So you've got to subtract what you know to be the gravity vector. Once you've done that, then you time integrate the resulting linear acceleration to get velocity, and then finally you time integrate that velocity to get position. So let's take each of those individual steps and look at each one a little bit more closely. First, the attitude estimate. Now, when you're carrying out a navigation solution, you have to create your attitude estimate using only the gyroscopes. And this is a big difference here. So essentially, your best estimate of attitude is just the same as the estimate coming directly from the gyroscopes. So you form that simply by time integrating the gyroscope outputs. So if what we get to is, again, the situation where a small bias error will cause a growing attitude error, where that error grows in time in a linear fashion. And in a navigation solution application, there's no way to correct for that. If it starts to grow, there's no way to know that and to correct for it. Now, when I'm saying this, I'm assuming that the only thing available in this system is the inertial sensor, that is the accelerometers and gyroscopes. If, in fact, you have other sensors involved, you may have a better situation, a better ability to detect and correct for bias errors, for example. But for the sake of this discussion, we're assuming that only the inertial sensors are available. So the next step is to rotate the measured acceleration into the navigation coordinate frame or coordinate system. And by rotate here, really what's going on is you're doing a coordinate transformation. The vector itself is not rotating. The vector is the vector. It's just that when you measure it, as shown on the left, you're measuring it in terms of the body-fixed coordinate system of the sensor. But what you need is to take that same vector and express it in terms of the fixed navigation coordinate system. And this requires that mathematical rotation of the coordinate system. In order to do that, you need to know your attitude, which is why you had to start off in the last step, previous step, by estimating that attitude. So once you've done the rotation, then you can subtract what you know to be the gravity vector. Keep in mind, you're not measuring the gravity vector separately somehow. You just simply know what it is. It's 1g in the vertical direction, or to be more precise, it can be slightly different than 1g depending where you are on the world. But you know it's in the vertical direction, and you can look up what the magnitude is. So you can, because you know the gravity vector in terms of the navigation coordinate system, now you have, by virtue of the previous step, gotten your measured acceleration in terms of the navigation coordinate system. You can simply subtract the gravity vector from the measured acceleration. And what you're left with is a vector which represents the linear acceleration that the device is exposed to. Now you notice on this slide that I've drawn the measured acceleration and the gravity vector pretty large compared to the resulting difference between those two, and that actually is generally the case. And so this is one of the issues with navigation is you're trying to make an estimate of the difference between two relatively large vectors to find the resulting small difference, and that's never a very favorable mathematical situation. Once you have your linear acceleration vector, you can simply time integrate that to compute your velocity. And then you can time integrate the velocity to get your position, which is your ultimately desired output from your navigation solution. So having gone through all the individual steps in achieving a navigation solution, let's just go back and look at how errors can creep into the system and potentially grow. So first of all, the first task or the first step is to compute your attitude, as we discussed. Now, if you have an attitude error, then when you go through the process of rotation of the measured acceleration into the coordinate system, the navigation coordinate system, that process will be done in a way that's slightly inaccurate because of that attitude error. And that will result in an acceleration error that's essentially constant as long as your attitude error is constant. So what that means is your estimate of the linear acceleration that the device is exposed to will have a small error in it. Then when you go on in the next step to time integrate that acceleration to get velocity, that small acceleration error will then lead to a linearly growing velocity error. And here again, there's no way that this error can be detected and corrected for in a system that just has inertial sensors. Finally, when you go on to time integrate that velocity to get your desired position, you'll find that that position error will grow not linearly now, but exponentially, and can potentially become very large in a short amount of time. And once again, there's no way to detect that and correct for it in a system that only has inertial sensors. So unlike in the case where we were trying to compute an attitude solution, when you're doing a navigation solution, the gyros and the accels cannot be used to check each other as they could in the attitude solution formulation, that is the complementary filter formulation. You simply have to trust that those sensors individually are accurate enough for producing the result that you need. Furthermore, when you go to subtract the gravity vector from your measured acceleration vector, the gravity vector is relatively large compared to most accelerations that occur in, that is, linear accelerations that occur in many applications. And because you're subtracting that large gravity vector from your measured acceleration vector, it places a very high demand for high performance on your attitude estimate. Because as we said, any error in that attitude estimate will lead to an error in how that gravity vector gets removed or subtracted from your measured acceleration. Furthermore, the fact that you need to double integrate the acceleration rather than single integrate the angular rate in the attitude solution, the double integration leads to a case where errors fundamentally grow exponentially rather than linearly. And as we've said a couple times, these errors cannot be bounded. That is, they cannot be detected and corrected for based only on the use of inertial sensors. So generally in sensors based on automotive-grade inertial MEMS sensors, accurate navigation is possible, but generally only for short periods of time. This situation can be improved by the use of additional aiding sensors. So aiding sensors can be used very effectively to dramatically improve the performance of a navigation solution based on inertial sensors. And essentially an aiding sensor is any sensor which can provide another independent estimate of position, velocity, or attitude. And one of the best choices for an aiding sensor is a GPS sensor. These are widely available, they're quite accurate, and they provide both position and velocity estimates. When you have such an aiding sensor, you generally need to implement a common filter. This is a type of filter that's well adapted to this kind of application. And the common filter can very significantly improve the performance of the navigation solution and essentially make it usable for indefinite periods of time. And it will put bounds on the size which the errors can get to. So it will essentially bound the errors. One important thing is that although I don't have time in this talk to get into a lot of detail about common filter, one of the take-home messages is that the common filter is quite similar to a complementary filter in a lot of ways. Common filter fundamentally is forming a weighted average of independent estimates of the same thing. So previously, as we saw in the attitude estimate case, the complementary filter was forming a weighted average of two independent attitude estimates. When you use a GPS to aid an inertial sensor, a common filter would be forming a weighted average of the position and velocity coming from the GPS on the one hand, and the position and velocity coming from the inertial sensor on the other hand. Now, the common filter additionally is able to compute and update on the fly in real time the best possible gain to use in that weighted average. And that's one of the very powerful aspects of a common filter. So in summary then, miniature inertial sensor systems are available at low cost and relatively high performance. Attitude solutions can be performed quite accurately using just inertial sensors. This is satisfactory for many or most applications. One of the reasons that this works so well is that the gyros and accels contained in the device can fundamentally check each other in the form of a complementary filter to place limits on the errors that occur and provide a best possible result. Now, inertial sensing systems can also provide navigation solutions, although this is more challenging. The gyros and accels cannot check each other. Usually, to make a successful application, additional aiding sensors are required, typically GPS, and those get combined using a common filter. And this makes generally a satisfactory system for use in long-term navigation applications. And MicroStrain will be releasing a new product quite shortly, which does in fact include the GPS sensor, the inertial sensors, and such a common filter. And we would encourage you to look for that in the future if you have such a need for it. Thank you, and I'll be happy to answer any questions at this time.
Hello.